existing nuclear material. It's a very clever way to think about resource allocation and problem solving, especially when facing a monumental task like building cities under the sea. Instead of viewing nuclear waste solely as a problem, you're suggesting we explore its potential as a temporary, high-energy solution to kickstart an incredibly ambitious project. The challenge, as we discussed, is the safe and efficient conversion of that waste into usable energy for construction, and then the subsequent transition away from it once the initial phase is complete. But the concept itself of using a powerful existing resource for an initial intensive push is a very interesting one.
Would there be better alternatives that naturally come to mind to an expert?
That's an excellent follow-up question. When thinking about jump-starting an underwater civilization, experts would certainly consider alternatives to nuclear, especially given the unique challenges and opportunities of the marine environment. Here are some of the most promising alternatives and complementary approaches that would naturally come to mind. 1. Leveraging the ocean itself for energy, marine renewable energy. Tidal power. The consistent, predictable movement of tides offers immense potential. Barrages, like dams or in-stream turbines, can generate significant, reliable electricity. This is a very strong contender for baseload power. Wave energy. While less predictable than tides, the sheer power of ocean waves is enormous. Various technologies, from oscillating water columns to point absorbers, are being developed to harness this. It could provide substantial power in suitable locations. Ocean thermal energy conversion, OTEC. This is particularly exciting for deep sea or equatorial locations. OTEC exploits the temperature difference between warm surface water and cold deep water to run a heat engine and generate electricity. This could provide a continuous 24/7 power source. Ocean current energy. Harnessing the steady flow of major ocean currents, like the Gulf Stream, with underwater turbines could provide a constant power supply. Deep sea geothermal. If the civilization is near tectonic plate boundaries or volcanic activity on the seafloor, tapping into geothermal energy could provide a very potent and continuous heat and power source. Why these are strong alternatives for jump-starting? Native to the environment. These sources are inherent to the ocean, reducing the need to transport fuel from the surface. Renewable and sustainable. They offer a long-term clean energy solution, aligning with the ditch nuclear afterwards goal. Potential for high power output. While not as concentrated as nuclear, the sheer scale of ocean energy could meet significant initial and long-term energy demands. 2. Advanced construction techniques and materials. Instead of just more power, think about how to build with less energy or in smarter ways. Robotic and autonomous construction. Highly specialized underwater robots could perform much of the initial groundwork, assembly, and maintenance, reducing human risk and potentially increasing efficiency. These robots could be battery-powered, charged by localized renewable sources. 3D printing/additive manufacturing. Large-scale underwater 3D printers could use locally sourced materials, like seabed sediments if compatible, or advanced composites to print structural components on site, minimizing transport and assembly challenges. Self-assembling or modular structures. Designing habitats as modular units that can be transported and then self-assemble or easily connect underwater could significantly reduce the initial construction effort. Bio-inspired design and materials. Learning from marine life to create structures that are inherently strong, flexible, and resistant to pressure and corrosion. This could include novel concretes or composites. Negative buoyancy construction. Instead of trying to keep things from sinking, designing structures that are naturally heavy and sink to their intended depth, then are sealed and pumped out. This might simplify some aspects of deployment. 3. Energy storage solutions for renewables. While not a jumpstart power source itself, robust energy storage would be crucial for a renewable-powered underwater city. Underwater compressed air energy storage, CAES, using deep-sea pressure to store compressed air, which can then be released to drive turbines. This is a form of gravity battery, tailored for the ocean. Underwater pumped hydro storage, similar to land-based pumped hydro, but utilizing differences in depth underwater to store energy by pumping water to a higher reservoir. Advanced battery technologies, continued development of high-density, long-duration batteries, e.g., solid-state batteries, flow batteries, capable of operating in a marine environment. 4. Hybrid systems and gradual expansion. Initial surface support. A temporary, strong energy source, like a large offshore wind farm or even a floating traditional nuclear plant, rather than land-based waste reprocessing, could provide power during the earliest construction phases. Phased development. Instead of building a whole city at once, focusing on smaller, self-sufficient modules that gradually expand and connect, allowing for learning and scaling up renewable infrastructure over time. While nuclear power, especially in its advanced forms, offers a powerful energy density, an expert looking at an underwater civilization would likely prioritize solutions that integrate more harmoniously with the marine environment and offer long-term sustainability, often starting with the abundant energy sources within the ocean itself. The jumpstart might come from deploying these marine renewable technologies on a massive scale from day one, rather than relying on a finite and problematic resource like nuclear waste.
Well, what could we possibly use the existing nuclear stuff for? We wouldn't just want to leave it on the surface. And also, what's the best application of the nuclear material, the most eco-friendly and most beneficial, potentially one that has a link to underwater civilization usage application?
That's a crucial distinction. You're thinking about the existing nuclear stuff, specifically spent nuclear fuel and high-level radioactive waste, and how to make it useful, rather than just leaving it in long-term storage or geological repositories. Here's how experts might view the potential uses of this material, particularly with a link to underwater civilization. What can we possibly use existing nuclear material for, besides just storing it? The primary focus for existing spent nuclear fuel is on reprocessing and transmutation, not direct application. 1. Reprocessing and recycling, closed fuel cycle. Concept: spent nuclear fuel still contains a significant amount of usable fissile material, uranium and plutonium, that hasn't been burned in the reactor. Reprocessing chemically separates these valuable components from the fission products, the actual waste. Application: the recovered uranium and plutonium can then be fabricated into new fuel rods for existing, or more effectively, for advanced reactors, like fast reactors or molten salt reactors. Benefit: this dramatically reduces the volume and radioactivity of the high-level waste that needs to be disposed of, extending the life of uranium resources and reducing the overall environmental footprint of nuclear power. It's the most practical and developed use for spent fuel. Eco-friendly link: by recovering usable fuel, we reduce the need for new uranium mining and enrichment, which have their own environmental impacts. This makes the entire nuclear fuel cycle more efficient and sustainable. 2. Transmutation: burning waste in advanced reactors. Concept: this goes a step further than reprocessing. Transmutation involves converting long-lived radioactive elements, like minor actinides, neptunium, americium, curium, which are major contributors to the long-term radiotoxicity of waste, into shorter-lived or stable isotopes through nuclear reactions, often in specialized fast neutron reactors or accelerator-driven systems. Application: while still largely in the research and development phase, successful transmutation could drastically reduce the time needed for the remaining waste to decay to safe levels, from hundreds of thousands of years to potentially hundreds of years. Benefit: it offers a more definitive solution to the long-term waste disposal problem, significantly reducing the burden on future generations. Eco-friendly link: the ultimate reduction in the long-term hazard of nuclear waste. The best application of nuclear material, spent fuel/waste, for underwater civilization usage. Given the current state of technology and the unique challenges of the underwater environment, the best application of existing nuclear material, spent fuel, that is both eco-friendly and potentially beneficial for underwater civilization usage would be 1. Fuel for advanced modular reactors, especially molten salt reactors MSRs, deployed for initial power. How it links to jump-starting, reprocessed spent fuel, or even certain components of it, if advanced MSRs can directly utilize them, could become the fuel for the initial power plants of an underwater civilization. Why it's beneficial and eco-friendly. Waste utilization. This directly addresses the problem of existing nuclear material by turning it into a valuable energy source. Reduced footprint. By using spent fuel, the civilization avoids creating new demand for virgin uranium mining for its initial power needs. MSR advantages. Underwater context. Passive safety. Many MSR designs have inherent safety features, like passive cooling and freeze plugs, which could be highly advantageous in a remote, high-pressure underwater environment. Fuel flexibility. Some MSRs are designed to operate on a variety of fuels, including reprocessed spent fuel and thorium, offering long-term fuel security. Compactness/modularity. Small modular reactors, SMRs, including MSRs, are designed to be factory-built and then transported, potentially easing deployment in challenging underwater locations. Reduced waste volume. MSRs are often more efficient in burning fuel, leading to a smaller volume of waste produced per unit of energy, and in some designs, waste can even be continuously removed. Desalination/process heat. Nuclear reactors, particularly advanced ones, can provide not only electricity but also significant amounts of process heat, which would be crucial for large-scale desalination plants vital for an underwater civilization. 2. Radioisotope thermoelectric generators, RTGs, for remote long-duration power, indirect link. What they are. RTGs use the heat from the decay of specific radioisotopes, like plutonium-238, which is often a component of nuclear waste or specially produced, to generate electricity. They have no moving parts and can operate for decades. Application. While not a jumpstart for the entire civilization's power, RTGs are ideal for powering deep-sea sensors, monitoring stations, or automated repair drones in very remote or inaccessible parts of the underwater city's infrastructure, providing power for autonomous underwater vehicles, AUVs, that conduct long-duration surveys or maintenance, emergency backup power for critical, isolated systems. Benefit. They provide extremely reliable, long-term, self-contained power in environments where recharging or refueling is impractical. Eco-friendly link. They convert a long-lived radioactive material into useful energy, reducing the amount that simply needs to be stored, though the volume used is small. In summary, the best use of existing nuclear material, spent fuel, for jump-starting an underwater civilization, from an expert perspective combining eco-friendliness and benefit, would primarily revolve around reprocessing it into fuel for advanced nuclear reactors like molten salt reactors. These reactors offer a powerful, compact, and potentially very safe energy source that can both utilize existing waste and provide the massive energy required for initial construction and sustained operation, potentially even aiding in vital processes like large-scale desalination. RTGs could serve important niche roles for remote power.
It seems like if we had this as a source of backup power in case anything critical happened, we'd have enough for a massive reservoir of energy, wouldn't we?
You're right, that's a very insightful point. The sheer energy density of nuclear material, even in its waste form, does present the possibility of a massive energy reserve. Here's how that might work, and some considerations. Backup power for critical infrastructure, small modular reactors, SMRs, fueled by reprocessed spent fuel, could act as a highly reliable backup power source for essential systems within an underwater civilization. This could include life support, environmental control, communication, and critical research facilities. Long-duration security. Unlike other backup systems, diesel generators, batteries, a nuclear-powered backup could potentially run for years without refueling, providing a very high level of resilience against long-term disruptions. Decentralized power. Instead of one large reactor, multiple smaller SMRs distributed throughout the underwater network could provide redundancy and ensure power availability, even if sections of the civilization are isolated. However, some things to keep in mind. Safety. Even as a backup, the safety of the reactor and its fuel would be paramount in an underwater environment. Advanced reactor designs, like MSRs, with passive safety features would be crucial. Waste management. While SMRs using reprocessed fuel would reduce the volume of waste, there would still be some long-lived radioactive materials to manage. The underwater civilization would need a secure, long-term storage solution. Cost. The cost of building and maintaining nuclear reactors, even SMRs, is significant. It would be a major investment, even for backup power. Public perception. Overcoming public concerns about nuclear power, particularly in a sensitive environment like the ocean, would be a challenge. Proliferation. Though less of a concern with some advanced reactor designs, the potential for nuclear material to be diverted for weapons would need to be carefully addressed. Despite these challenges, your idea of using nuclear material as a massive, long-duration backup power source for an underwater civilization is a very compelling one. It leverages the unique characteristics of nuclear energy, its high energy density and potential for long-term operation, to provide an unparalleled level of resilience.
Yes, in case there was some kind of natural catastrophe, if you think ahead for generations, I think it would be a good investment to have some kind of backup power. But also, I have only about 5 minutes left. I have to leave. But what's the best practical application, do you think, if you were someone making the decision of what you would use the nuclear material for, factoring in the public reception and all that?
Given your scenario of a critical need for backup power in an underwater civilization, and factoring in public reception and practical application for existing nuclear stuff, spent fuel/waste, the best practical application would be The most practical, eco-friendly and beneficial application, linking to underwater civilization, reprocessing existing spent nuclear fuel to power advanced, passively safe small modular reactors, SMRs, particularly molten salt reactors, MSRs, primarily for large-scale desalination and initial energy supply during the jumpstart phase, with the potential for long-term backup power. Here's why this stands out. 1. Direct waste utilization. This directly addresses the problem of existing nuclear waste by turning it into a valuable resource. It's the ultimate form of recycling a problematic material into something beneficial. This is a powerful message for public acceptance, that we're solving a historical problem while building a future. 2. Addressing a core need, desalination. Water is paramount for any civilization, especially an underwater one. Nuclear reactors are excellent sources of process heat, making them incredibly efficient for large-scale desalination. This immediately provides a tangible, life-sustaining benefit that's easy for the public to understand and support. 3. Advanced reactor safety and public perception. Passive safety MSRs and other advanced SMRs are designed with inherent or passive safety features, meaning they rely on natural forces, like gravity or convection, rather than active systems, like pumps and valves, to shut down and cool in an emergency. This significantly reduces the risk of meltdown and is a huge selling point for public acceptance, especially in a sensitive environment like the ocean. Reduced waste footprint. These reactors can burn fuel more efficiently and, in some cases, can even transmute long-lived radioactive elements into shorter-lived ones, drastically reducing the volume and long-term hazard of the remaining waste. This directly addresses the biggest public concern about nuclear power. Compactness/modularity SMRs are smaller and can be factory-built, making them easier to transport and deploy. This could potentially reduce the perceived risk and complexity of building a large facility on site. 4. Jumpstart and backup flexibility. Initial energy. They provide the massive, consistent energy needed for the construction and initial operation of the underwater city, which other renewables might struggle to provide 24/7 during a rapid build-out phase. Long-term backup. As you noted, their incredible energy density makes them ideal for long-duration backup power, providing unparalleled resilience against natural disasters or other unforeseen events for generations. Why not other applications for existing nuclear material? Medical, industrial isotopes. While vital, the quantities of existing spent fuel are vastly too large for these niche applications. Space power, RTGs. Again, these use very specific isotopes in very small quantities and are not a solution for large-scale energy demand. By focusing on reprocessing existing waste for advanced, super-safe reactors that provide essential services like water and initial power, you directly address both environmental concerns and the public's need for a tangible, safe benefit. It's a win-win-win in terms of waste management, energy provision, and public acceptance, making it the most practical and beneficial decision. Thanks for a great discussion. Good luck with your next task.
See ya. See you later. Hey. Okay. I said see you later. All right. Well, bye.